a few terms I'll need a couple slides to explain. When it comes to the table, I want you all to focus on this guy here, ionization power. From looking at the table, right, alpha seems to have a high ionization power, while beta is fairly low, and gamma is the weakest when it comes to ionization power. So you're probably asking yourself, well, what is ionization? And some of you kind of know what is ionization, but you notice I use the word power. So that phrase, ionization power, might seem a little bit strange, but I will explain that entire thing in a little while, in about 2 minutes. The other thing that I want you to focus on that's very popular in the exam is what it takes to stop alpha, beta, and gamma. Let's say somebody comes up to you with an alpha gun, right? Just like how we could have a real gun. Well, what can stop a real gun is something like what? A bulletproof vest. A bulletproof vest would prevent a bullet from penetrating and going into you. Well, if somebody comes up to you with an alpha gun and said, hey, stick him up, and shoots you with alpha particles. Alpha particles, you can think of it as being very, very weak. It only takes paper or human skin to actually stop it. Now, I want to focus on the human skin for a few seconds. Even though skin can stop alpha, it will get damaged in the process. For example, just like a bullet. When a bullet hits a bulletproof vest, the bulletproof vest stops the bullet, but it gets damaged in the process. So if you had to choose between paper and human skin, choose the paper, right? It's okay if the paper gets a little damaged, but obviously it's not okay if your skin gets damaged. To stop beta, beta is a little more powerful, but when it comes to penetrating stuff, right? It only takes about 3 millimeters thickness of aluminum to stop it, right? That's fairly reasonable. But gamma, well, here's a problem. If somebody comes up to you with a gamma gun and shoots you, it's almost impossible to stop gamma. You can use lead if you wish, but 1 centimeter thickness of lead will only reduce it by a half, right? And as you all know, lead is really, really, really heavy. So having a really thick lead suit is going to be impractical. Now, some textbooks will say, right, and they're right, instead of saying using lead to stop gamma, some of them might say use concrete. But when they say concrete, it's not just a thin layer of concrete, you're talking like 4 meters thickness or 5 meters thickness of concrete to stop or even just reduce the gamma, right? So let's move on now, and I want to focus on the ionization power and what we mean by this. So let's move on and let's see what the next slide is about. All right, so we're going to use this diagram here to explain what ionization is. First of all, right, let's do a count up of all the protons and neutrons and electrons. So how much protons do we have here? You think you can do a quick count? The protons are the positive one. Do a quick count and let me know in the chat. How much protons do we have? I'm doing a quick count up here on my end. Oh, so a lot of people are saying it's 6. Let's make sure. 1, 2, 3, 4, 5, 6. Right. So there are 6 protons. Of course, the protons are what? Positive. Let's see how much neutrons it has. Let me do, that's the red ones, right? Because you notice the red ones, I did not put a charge because that is because neutrons have what? Well, no charge. 1, 2, 3, 4, 5, 6. Now tell me something. Is it is it necessary that we always have the same amount of protons and neutrons? You see how we have 6 protons and neutrons. Is that always going to be the case? The answer is no. Today's diagram is just pure coincidence that there's the same amount of neutrons and protons, but in most cases, they're not really the same amount. Now, for electrons, in a normal atom, the protons and electrons are supposed to be equal. The positive charges are supposed to balance out what? The negative charges. And if we do a counter, 1, 2, 3, 4, 5, 6, it has 6 electrons, and we all know the charges what on electrons are negative. So because the positive is equal to the negative, right? The overall charge, I'm talking about the, if you do your maths, 6 positive, 6 minus 6 is what? 0. So this is what we hope to have in an atom. We always hope that the overall charge is 0. But what is ionization? Well, let's take an alpha particle and let's shoot this atom. So we take an alpha particle here and it zooms towards that atom. Tell me something. I want you to picture this in your head. Pretend that you are balancing on one foot and you have 6 eggs in your possession. You have 2 in your hand, like 4 in your hand, and you're balancing one on your nose and you're balancing one on your head. Pretend those eggs are the electrons. So you have 1, 2, 3, 4, 5, 6 electrons / eggs. And somebody runs into you, just like how this alpha particle is running into that atom. Do you think any of the eggs will fall? Well, what will most likely happen? Do you think some of the eggs will fall off you? Right? Most likely, yes, most likely some eggs are going to fall off. So this alpha particle, it hits the atom and it hits off one of the electrons. So one of the electrons gets bumped off. Tell me something. Is the overall charge 0 now? Let's do the maths. It still has 1, 2, 3, 4, 5, 6. So it has 6 protons, but now it only has 1, 2, 3, 4, 5. It only has 5 electrons. So when you do the maths here, 6 minus 5 is actually positive 1. The overall charge is not 0. It is what? Positive 1. Whenever an atom has a charge, an overall charge that is not 0, you call this type of atom an ion. And the process of hitting off electrons or making the amount of positive more than negative, or the amount of negative more than positive, is that process is called ionization. Now the question is, what is ionization power? Well, remember there were 3 particles, alpha, beta, and their old friend gamma. It just so happens alpha is really, really good at hitting off electrons, right? So you come like, pretend that you are balancing on one foot again with all the eggs. Alpha come like a big person running into you. And because he's so big, and of course he's powerful, right? He will do a very, very good job at hitting off the electrons. So he's really, really good at that job. Beta comes like a smaller person, like a toddler. So a toddler is running towards you. Obviously, the toddler does not have as much power as the grown-up, the big person. But obviously, if a toddler hits you hard enough, you could lose your balance and one of the eggs could fall off. And gamma, well, he is the least powerful at hitting off electrons. I'm talking about just hitting off the electrons. Gamma comes like what? Like a feather coming towards you. Now, most likely, if a feather hits you, it's not gonna make you lose an egg. But you know, it can fall on you and tickle you, and then of course you can lose focus. But you know, that's a really, really, how you say, improbable case. It can only happen once in a while, right? So everyone think they understand what ionization power is now. It's the ability or how good a particle is at hitting off electrons. And it just so happens gamma is the best at doing it. Beta is okay-ish at doing that. And gamma, well, he's the worst at doing that. It's like you could almost depend on him not to hit off any electrons. All right? All right, now you don't have to take down anything here because the term ionization, I just want you to understand it, and it's going to come up so much other times, especially when we're doing the past papers and whatnot. All right, so I'm going to move on to the next slide, right? And let's see what's next here. Right, let's see how much you remember from this table. What does it take to stop alpha and beta? I made two slight mistakes here. You notice the alpha is stopped by paper. This diagram shows that beta can go through paper, but it's stopped by perpex. And this one shows gamma could go through almost anything, but when it hits the lead, it still goes through, but it's a little bit reduced. I made two slight mistakes here. What am I supposed to put here? What are the two things that can stop alpha? Right, paper or human skin. And this one here, now why perpex can stop beta? This is not the one for the CXC syllabus. What am I supposed to have here? What will stop beta? 3 millimeters of aluminum. You see this diagram here? It's a standard diagram, not only in a textbook, go through any physics textbook, you will see this diagram, but it comes so much times in the CXC exam. I'm going to give you a 3 minutes to draw this diagram. Memorize it. It really helps you to figure out what can stop alpha, what can stop beta, and what can stop gamma, right? Right. Right? To be more accurate here, 1 centimeter of lead will reduce it by a half, right? So if you want to put the thickness of this, you could probably put 1 centimeter, right? Usually in most textbooks, it will have 1 centimeter thickness of lead, right? But the point is, the thicker the lead, the more it will reduce the gamma, but nothing can really, really stop gamma. You can only reduce it. Right, so let me know when you are finished. Slide. All right, so here's the text. Read those, let me help you read these two statements that are on the board here. An atom is mostly empty space. We're going to explore what that means just now. Do you all agree with the second statement that the center of an atom, we're talking about the center of the atom, is positive? I think we had discussed this last week. Because remember, the center of the atom only has what? Protons, which are positive, and it have what? Neutrons. The center is called your nucleus, as we all know. But since the center only has positive charges and something with no charges, the positive charges win the battle because they have no competition. And now that's really, really important, that to know that the center of an atom has an overall positive charge. But how did scientists figure that out? Remember, most of these stuff were figured out quite in the 19th century or in years like 1903 or 1931, where there were not very, very powerful microscopes. So you couldn't actually zoom into an atom and physically see the center of the atom, right? You couldn't physically do that, right? So I have to explain to you the experiment that they performed to kind of figure that out. Also, what do we mean by an atom is mostly empty space? You see a lot of diagrams. You see when you go in the textbook, you know, they just draw an atom like this. You saw one on the board just now, right? You'll see the nucleus and then spinning around it. It has the electrons. This diagram is really gives you a false impression of what an atom looks like. In real life, an atom doesn't look anything like that. You know? We just draw it like that just to make it kind of easier to grasp the concepts. The first thing and most important problem with this diagram is that when you draw the nucleus, look at the distance between the nucleus and the electrons. Do you all agree that in this diagram, the electrons look close to the nucleus? Even if I draw a second shell around it like this, do you all agree that it gives the impression that the electrons are, you know, kind of close to the nucleus? It's relatively close, right? In real life, it's not like that. Huh? And there's a reason they don't draw it lifelike in your textbooks. But I'm going to show you, give you an analogy of how it actually looks in real life. Everybody knows what a football field is, right? I think everybody has a general idea of how big a football field is. What we are going to do is take an atom and we're going to use a machine and magically make it larger. So we're going to take an atom and make it as big as a World Cup football field. Let's pretend this is the football field here. Right? The goal on one side, the goal on the next side. We are going to take a grape, those same grapes that you buy, those purple grapes you buy in the grocery, and we're going to put it in the center of the field. We are going to assume, right, that grape is the center of the atom, the nucleus. Do you all know where the first electron will be? The first electron will not be here, you know. It will not be here. It will not be here. It will be quite over here. Try to imagine that scenario. The nucleus is the size of a grape. And the first electron is quite on the edge of that football field, which means the next electron is even further away. And if you have a third shell, it's even further away. Which brings us to this problem now. Let me erase that field now. What does it have in between here and here? So this electron is revolving around that grape. What do we have in between here and the orbit? Who can tell me what we have between the nucleus and the orbit? Correct. Nothing. Empty space. Which means an atom is mostly empty. Well, here's something to think about. You are made up of what? Atoms. Which means you are mostly what? Empty space. You are full of holes. Trillions and trillions of holes, right? You are mostly, well, I know this sounds kind of depressing, empty. All right? I don't have a better word. All right? So it's just, but we don't see all the holes in our, like, if you look at someone's face, right? You won't see all the spaces in their face because our eyes are just not powerful enough to zoom into all of that space. So we appear what? Solid. All right? So imagine this now. How did scientists figure that out without a microscope? You ever have been so bored that you ever sit down and think about these things? Or are you all too occupied playing, what do you call them things? Like PS3 or PS, well, whatever, which one out now. Right? So if you ever wondered about it, right? And oh, just to answer one question, even though you're not supposed to be asking questions, I will right at this point in time. Atoms they don't actually touch each other because in a sense, because if one is orbited, one is next to it. It's not like this nucleus touching this nucleus, right? Right, but that's a discussion for another time, right? Whether atoms touch each other or how close they are to each other, that's really, really in-depth conversation for a different point in time, okay? So let's move on. I'm going to try to explain how scientists figured out those two things. Oh, sorry. I didn't give you all a chance to take down the note on the table, on the paper. Everybody has heroes, right? You see these three guys here? I would consider them to be heroes. And you are probably asking, who are these guys? Well, you met the first guy here already. This was, if you had done your revision, right? Do you all remember what's the name of this person here? What's his name? His picture was up last week when we were doing the history of the atom. All right, this is Ernest, and his last name is over here, Rutherford, right? A very famous scientist, a physicist, okay? Now, let me give you the story, right? These three guys here in front of you, they were basically, but mostly responsible for figuring out those two things about the atom we just mentioned. They basically figured out that an atom is mostly empty space and that the center of the atom had to be positive. Let me give you who was in charge of who here. The person who was in charge of the whole experiment was Ernest Rutherford. He was the professor at the university. And there were two, from what I understand, right, two students underneath him. And under the guidance of Rutherford, Hans Geiger and Ernest Marsden, they built a certain device. And you all see the picture of the device here, right? And using this device, they were able to make the two conclusions. I'm not asking you, the only thing I need you to take down here is this. And this experiment did not take 1 day, it didn't take 2 days, it didn't take 1 year. It went on for almost 5 years. So for 5 years, these guys were in and out of the lab, in and out, taking measurements, doing experiments, performing tedious calculations. Let me know when you finish taking on this small note, and I'm going to explain how this device worked and how it enabled them to, to figure out an atom is mostly empty space and the center was actually positive. It shouldn't take more than 20 seconds there. All right. Now, to understand how that piece of equipment works, we have to go through some background theory. Now, I know that the piece of equipment that I just showed on the board here, the board, I keep saying board, on the screen, you're probably wondering how large it is, right? From what I understand and from certain, researching a little bit, it's about 1 meter in length, right? So it wasn't a really huge piece of equipment, but very useful. So let's go through some background theory here. Let's talk about charges. Now, I'm not too sure how much you did in school already, but charges either attract or charges either repel. If I put two positive charges together, will they attract or will they repel? What do you all think? Well, I think the answer is on the screen there. It wasn't supposed to be on the screen, but I left it there by mistake. Right. Because you have two same charges, at the end of the day, similar charges repel. So two positive charges would push each other away. What about two negative charges? So I bring two negative charges together, attract or repel. They will definitely repel. And of course, The last scenario is they're going to attract because one is positive and well, one is negative. Opposite charges attract. Okay. So take down everything on the screen, right? Take down the 3 diagrams and take down this little note here, right? Even if you know it already, no harm in taking it down a second time. Let's slowly build up to how that piece of equipment worked. So let's see what's next on the list here. All right, so here's what now. We're going to put what we just learned into play. Keep in mind, opposite charges attract, like charges repel. Now, let's just pretend that you have a positive charge here, and he's stuck basically in the middle of the screen. Look at what's going to happen now. Something is going to fly across. So a positive charge begins to walk across the screen, right? Now, I want you all to look at the distance between this positive charge and this positive charge. Obviously, the distances between charges will make a difference. If one charge is really, really, really far from another charge, do you all think that the 2 charges will interact with each other? Well, what are your thoughts on that? Say I have a positive charge in Kunupir, in Trinidad, and there's another positive charge in Paris. Do you think those 2 charges would even acknowledge each other? The answer is no, right? So the closer 2 charges are, the more likely they are to interact. So remember, this charge was flying across the screen. Do you think he will be repelled, or do you think he will just go about his business? What do you all think? The yellow one I'm talking about. Do you think he will make it to the end of the screen, or will he be repelled? He will, right? Somebody said it the right way. He will just go about his business. So the yellow, let me use yellow for yellow, right? So he just floats across the screen and he goes straight across because we're assuming that this distance is really, really huge. Look at what happens now. Another charge decides to walk across the screen. Right. You notice I'm trying to depict that he's close to the center charge. Do you think he will make it across the screen? What do you all think? Yeah, I don't think he will make it across. It comes like somebody is running. Try to picture this in your head. Somebody's running close to you, so they're running real fast. And then when they reach by you, I'm not saying to try this, you push them. Try to imagine how they will be pushed. Try to imagine what their line of motion might look like. The person, when he's running across, because you push him, he doesn't go 90 degrees. Do you think this is a more likely depiction of what will happen? He would slightly curve upwards, right? Because remember, these 2 charges are repelling. So when the green charge comes close to the pink charge, the repulsion comes like a push, and he makes a kind of curved motion, right? He's been deflected. That's a nice word someone used over there. All right, but let's look at another scenario now. Look at this scenario. The blue charge, you all notice the slight difference here? The blue charge is not far away. He's not close. He's a different scenario. He comes directly in line with this. Now, let me explain what happens. A lot of people are thinking this. Well, since the blue charge is directly in line with the pink charge, the 2 are going to hit each other like marbles. That doesn't normally happen. Let me imagine this. The blue charge is coming closer. As it comes closer, the repulsion gets larger and larger and larger. It gets larger. I keep saying it over and over, right? Larger and larger. Eventually, the repulsion gets so large, he gets pushed away in the opposite direction. It's like a spring getting compressed and compressed and compressed. And eventually, you're not strong enough anymore. And the spring pushes you back. You think you all can imagine that? But that only happens if this positive charge is directly in line with the other positive charge, right? I want you all to draw this diagram of the three scenarios. In one of the scenarios, the charge just moves across the screen. That's the yellow one, because he's unaffected by the other positive charge. When it comes close, he gets pushed to the side. But when he's directly in line, a very rare scenario, the repulsion is so great, he gets pushed back. All right. So here's what, right? We're going to pretend that we can shrink ourselves and we're going to go inside that small machine. Let me explain what we're going to find inside that machine. Inside the machine, you're going to find a radioactive source. Remember, a radioactive source shoots out radiation. And there are three types of radiation: alpha, beta, and gamma. I am letting you know that this radioactive source is shooting out positively charged radiation. So go back in your notes. If I tell you that it's shooting out positively charged radiation, which one am I talking about? Alpha, beta, or gamma? Send your answers on the chat. Go back in your notes. Which one of the three of them are positively charged? Jeremiah, correct. Nikin, correct. Sadiq, Angelo, correct. Come guys, go back, go back. Remember, one of them is positive, one of them is negative, and one of them has no charge. Right, it's alpha I am talking about, right? So this here is an alpha source. Simply put, it's just shooting out alpha. So it's going to shoot alpha at this yellow piece of paper, but it's a special piece of paper. This piece of paper is called gold foil. Its name suggests exactly what it is. You know, in your kitchen is have aluminum foil paper. That's the shiny piece of paper. But instead of it, this here, instead of it it's made up of gold. So it's like a thin sheet of gold, right? It's gold foil. And here's what happens in the experiment. Let's say we're going to take the alpha source and shoot this gold foil. So this cowboy here, he comes like he's the person shooting alpha, right? And we're going to pretend we have 4 people here. One next to the cowboy, one right behind the foil paper, and 2 to the sides. Now, here's the amazing thing in this experiment, right? We know, I'm trying to use imagination again. If you have a gun and you shoot a piece of paper, so let's pretend you have a machine gun, right? And you're shooting a piece of paper. Will you see holes in the paper? Yes or no? Well, what would you expect to see? Right? Definitely yes, right? Anybody who has even if they've never seen that happen, right? You know, if you have a piece of paper and you take a machine gun and you shoot the paper, you're going to see a whole set of holes. Something similar is happening here, right? You have a gold foil, like a sheet of paper, and you're shooting stuff at it. Now, here's the thing. The guy behind here, he gets shoot. But that's expected. If somebody stands behind a piece of paper and you have a machine gun, obviously that person behind the paper is going to get shoot. That's expected, right? But here's the problem. And the person is only aiming at the foil paper. But you know what happens in this experiment? He gets shoot, and he gets shoot, and he gets shoot. Don't you all find that strange? The person is aiming this way. The most obvious person gets shot. But why is person, I'll call him A, but why is person B, and why is person C, and even worse, why is person D also getting shot with bullets? Right? So I know you're going to come up with some crazy theories in your head. Right? You're going to say the bullet got deflected. Some of you all are pointing to that movie called Wanted with Angelina Jolie, where the person could curve the bullet. All kind of madness, right? Some of you all are saying it's hitting person A and bouncing off person A and hitting person B, right? So we're going to have to explain why that happens. And that's almost the same thing that was happening in the experiment. Instead of bullets, the device was shooting alpha. The alpha went straight through the paper, well, as expected. It hit right behind the paper, but apparently it was also hitting the sides of the room where person B and C. And then it was also seemed like it was bouncing back and hitting person D. But here's an even bigger puzzle. Just like with the machine gun that's shooting the paper, when you shoot the paper, you would expect to see a lot of holes. And we know it's going through the paper because person A is getting hit. But you know what happened? When they looked at the piece of paper, they saw no holes. So imagine this puzzle and pretend you are them in that scenario. You shoot something at a piece of paper. We know it went through the paper, but the piece of paper has no holes. It almost sounds like voodoo, like black magic, right? So let's explain why that scenario happens, right? Now, I need for you all to draw this scenario for me, right? So draw this out. You don't have to draw the world's best drawing, right? And you don't have to draw the cowboy if you don't want to. But let me know when you're finished with the diagram. All right, so when the two guys were doing the experiment, Geiger and Marsden, all they did was look into the device, and this is all they were basically seeing. They were seeing sparks here, like I said, they were seeing sparks to the side, and they were seeing sparks over here. To be a little more precise, they were seeing the most sparks directly behind what? The foil paper. They were seeing a medium amount of sparks to the sides. And where the person D is standing, there was a very few sparks, which means most of the alpha was hitting here. Only some of the alpha was hitting the sides, and only very few were reaching this point. And from watching those observations alone, I know some of you are still puzzled, right? From watching those observations alone, they came to the conclusion that the center of the atom was positive and an atom was mostly empty space. But how? How much of you all would have really come to that conclusion if you were back in 19 something? From just looking at those three things, would you honestly come to that conclusion? So, and of course, some of the brightest people in the world may not have come to that conclusion. Imagine the three of them sitting down in a room discussing the observations and the amount of talks that went into the discussion. And I'm going to show you why they came to that conclusion, right? So I'm going to switch here, right? Imagine this scenario, right? Here we have a fly and here we have a frog. So y'all can read what's going on here, right? Apparently the frog ate his friend. And now the fly is out for revenge. So he brings a gun, right? Now, I don't like using real guns as pictures, right? So I have this like toy gun here, right? So the frog decides to take cover. So he goes behind that fence. Do you think the frog is safe? What do you all think? Right? No person in a right mind is going to take cover behind a fence. Quick question, why is that frog not safe? Why is the frog not safe? Right, a lot of people have got it off the bat. That fence is full of holes, right? It's not a solid piece of fence, right? I mean, it has a little bit of protection. You could even say that the fence is mostly empty space. So when the fly begins to shoot, you can be more or less sure most of it would go straight through the fence. Do you think it will leave any holes in the fence? My answer to that is no, because the fence already has a bunch of holes, right? It came with holes. So that is one thing to note. That comes like the gold leaf just now. And let me go back to it, right? The reason that the alpha went straight through is because this was mainly made up of, well, it's made up of atoms. And the only way it could have gone straight through without leaving any holes is if the atom was mostly empty space. And if it already had holes, right? It's just the holes are there. It's just we cannot what? See it, right? So, and of course, that came up, I'm sure that came up in their discussion, right? So that's the first thing there. So that is why person A got the most bullets, right? Because atoms are made up of mostly empty space and it already came with holes, right? But why did it go to the side? Imagine this. You see all these pink things here? Let's pretend those are alpha particles. And it moves towards the atom. Now look at this diagram carefully. Only the center of the atom is positive. Everything else is mostly what? Empty space. You notice some of the atoms that they're moving across. You notice a lot of the pink ones are outside the yellow region. We're going to consider everything in yellow, anything in that region, to be close to the atom, close to the nucleus, such that it's affected by the nucleus. Quick question, do you think the majority of them will be unaffected by the nucleus? Yes or no? The answer would be yes, because look at it. Anything outside this yellow region, he outside, they will never be moving straight across. So the majority of these atoms will just move straight across and end up where person A was standing. This is why over here had the most sparks, because an atom is mostly what? Empty space. For the few that ended up in the yellow region, remember, the center is positive and alpha is also positive, right? Those that end up in the yellow region will be deflected to the side. Remember, we saw that just now. Two positive charges will be deflected. And the only way it could have been deflected is if the alpha and the center of the atom had the same type of charge. Now, they knew alpha was positive. So the only logical conclusion that could have been drawn was that the center of the atom was also what? Positive. That's the only way a deflection could have occurred. And for the very few that came directly in line with the nucleus, bounced straight back, which kind of inferred that the center of the atom even further was positive, because you got deflection as well as complete what? Repulsion. So let's summarize everything. You don't have to draw this one, right? Let's just summarize everything they just learned from this scenario. This is what they learned. Most alpha particles went straight through unaffected because they were far from the nucleus. I think I spelled, owing to the atom being mostly empty space, or another way of saying this is that most of the mass is concentrated to the center of the atom, meaning that that's another way of saying, hey, an atom is mostly empty space. The other thing that was learned was a small number of particles were deflected due to repulsive forces to the side as they pass close to the nucleus. Of course, this indicated that the center of the atom and alpha particles had the same type of charge, which was positive. In the exam, you have to memorize this, and you have to memorize this. They will most likely ask you what was learned from the Geiger-Marsden experiment. Okay? Let me know when you finish with everything in red. See what's next? All right, so we're gonna get how you say, move into some definitions here. So what is radioactive decay? Let's talk about each one here, right? So last week we spoke about atoms, and I told you last week that atoms can be unstable, and I gave you a reason for it, right? Sometimes an atom has too much neutrons in it, and it causes it to be what? Unstable, or the nucleus itself could have too much energy. So usually, but in both cases, you consider the atom to be unstable, whether it have too much energy or it has too much neutrons. So what the atom will try to do is emit radiation such that, well, when it gives off alpha, beta, or gamma, depending on its choice, it will hope to become stable. It's like a sick person vomiting, trying to get rid of something to achieve the feeling of feeling good, right? So just to put some technical language in it, because the examiner will want some technical language. Radioactive decay. Radioactivity is a spontaneous disintegration. Spontaneous disintegration. Disintegration just means it's giving off something of an unstable atomic nuclei by emitting particles of energy. And these particles of energy that they're talking about, it's either alpha, beta, or gamma. Take down this definition. Let us go through all one at a time, just in case, right? Oh, but the second one is pretty easy. I kind of set it up here already, right? In radioactive decay, either alpha, beta, or gamma can be emitted, right? I'm not reading it here. The third one is pretty easy. All the third one is saying is the more radioactive something is, the more alpha, beta, and gamma it will emit, which makes more sense, right? Which makes sense, meaning that you can have two rocks. One could be very, very radioactive, or one could be slightly radioactive. Obviously, the more radioactive one is more dangerous because it's shooting out more alpha, beta, or gamma, right? You can take down the fourth one, but from going through the past papers and whatnot, I've never seen them ask for the ratio of neutrons to protons, right? But take it down just in case. When we're going through some older past papers, you might see this piece of theory coming up. Let's move on to the next slide. All right. So we're going to have something called decay equations. But before we actually do this is going to take a little while. I want to explain something from last week here. Here we have an atom, right? Remember last week I told you that when you have an atom, there's a number on top here and a number underneath here. One is BZ and one is BA. One is the one on top is what? The mass number. And the other one underneath, well, sometimes we call it what? The proton number, right? Better known as the atomic number, right? The different teachers call it different things, and I gave you both names last week. For this atom here, how much electrons will it have? I know I didn't draw in the electrons, but could you just quickly tell me how much electrons I'm supposed to draw in? 4, right? Because if it have 1, 2, 3, 4 positive charges, then to balance it off, obviously I need what? 4 electrons. Could you all do me a quick favor? Let's call this atom X. I want you all to put in the top number and the underneath number for me quickly for this particular atom. Remember, the underneath number, the proton number, is the amount of protons. So it's just 1, 2, 3, 4. That's the red. So the underneath number is 4. But remember, the top number is the amount of protons added to the neutron. So it's everything in the center. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Some of you all count the blue one wrong, right? I know it's just a small miss. You just see it wrong, right? But I know you're already meant to put 9. So this is how you represent this element here. Quick question. Do you all know the difference between carbon and nitrogen? Well, if somebody were to ask you, what's the difference between carbon and nitrogen, or silver and gold, or iron and gold? Now, obviously, in terms of iron and gold, or silver and gold, we know one is more expensive than the other, right? There are a lot of differences. But on an atomic level, the main difference between gold and iron is that gold has a different amount of protons and neutrons than what? Iron. My point is this, right? Let's say you have an atom X. Let's just pretend, I don't know which element this is in the periodic table. I really can't remember, right? But let's say this is, just for simplicity's sake, let's say this is lithium, right? Let's just assume it's lithium. So according to my diagram, lithium has 4 protons and how much? 5 neutrons. Let's just say that for some, I have a magical device and I remove one of the protons. Sorry, one of the protons. Oh, God, that's not, guys. 1 second. I remove one of the protons. Let me say I remove two of the protons. If I remove two of the protons, obviously I have to remove what? Two of the electrons. Is this still lithium? What, can I still call it lithium? The answer is no. It's not even a lithium ion. If I only remove the electrons, then you could call it what? An ion. But look what I did. I also removed some protons, which means this is a totally different material, a totally different what? Element. Which the point is this: whenever an atom loses protons and neutrons, I'm not really talking about the electrons, right? I'm already not too focused on electrons. Whenever an atom loses protons and neutrons, things from its nucleus, it will no longer be the same element. You have to call it by a different name. To put that in perspective, if you take an iron atom, like iron, right? Iron has a certain amount of protons and neutrons. If you were to add some extra protons and some extra neutrons, you could change it into gold. Scientists haven't figured out how to do it as yet, right? But if you were able to add in extra protons and neutrons, you would get a totally different element. And if you add the right amount, you could get gold, you could get silver, you could get lead, right? Everybody with me so far? If you change the amount of things in the nucleus, you will get a totally different element. Confirm with me on the chat, guys. I want to make sure this is going to be real important later on, right? And I'm not going to have time to stop to re-explain it, right? All right. Next thing now. If I have an atom, you'll remember, so I'm not too sure if I explained this last week, right? Remember this element called helium, right? Helium has two protons, two neutrons, and two what? Electrons. I think I went through this last week. Remember, I tried to explain the difference between helium and alpha. Alpha is when you strip away both electrons and you only remain with the nucleus. And of course, you make it very fast moving. Tell me what number to put on top here and tell me what number to put underneath here. Remember how we did this example just now with X? We had a top number and an underneath number. What number would we put on top for alpha and what number would we put underneath for alpha? Right, so a lot of people are telling me 4 and 2, and that's correct. The underneath number is the amount of protons, whatever we are talking about, in this case alpha. It has 2 protons and 4 particles in all, 1, 2, 3, and 4. For beta, what would be the top number and what would be the underneath number? Remember, beta is a fast moving electron, but we still need to put a top number and an underneath number. When we're talking about it, when we start to put it into equations, we need a top number and an underneath number. Seen plenty wrong answers. All right, so let me explain this. Beta is a fast moving electron. Whenever we're using this format, the top number is always the amount of protons plus what? Neutrons. Beta has no protons and it has no neutrons. So guess what would the top number be? 0, right? Now the underneath number, we can't put 0 in today's case, right? Remember, the underneath number is what? The amount of protons. But does beta have any protons? The answer is no. It has an electron instead. So you put -1. It comes like the opposite of a proton, right? But if it doesn't make too much sense, just memorize this. For beta, the top number is always 0, and the underneath number is -1 because it has no protons, but an electron is the opposite of a proton. And gamma is pure energy. Gamma has no particles. So guess the numbers for gamma: 0 and 0. Right, let's take down these three. I'll summarize it here. Alpha is 4, 2, beta is 0, -1, and gamma is 0, 0. This is all I really needed to take down for the time here. And homework should be much easier to explain this time. It's the second time around. Right. So the homework, as usual, is to go when I'm going to eventually upload this video, and you all by now know where to get the video, right? You go on the school website and you click on summer recorded classes, scroll down. Tomorrow you will see the link to access this class. Please watch it through again. I'm sure that you may have missed some notes in between, and it's always good to see it a second time. For those who did not review the forces video in the physics classroom, please finish it by next week. I just want to give you a small mini quiz on some of the beginner's theory on it. And of course, inside the physics classroom, feel free to watch any videos that you want to watch, right? So if you know in September, your teacher is going to start a certain topic, find the topic and feel free to go through the videos. For those who understand what the homework is, you are free to leave. For those who are still confused, stay back and I will try to go through it in more detail. All right? When you go to the school website, look for the menu. You will see summer recorded classes. When you scroll down, today is what, Tuesday? You will see last week recording over here. By tomorrow, today's recording will also be up, right? So that's the first thing. And we also have a physics classroom. So when you go in the physics classroom, you will see a video called Forces, something to do with forces. Let me see if I can find it here. Refraction theory. For some reason, I can't find the forces video. Anybody seen the forces video there? I passed it. Oh, Lord. Refraction wave. Oh, look at it. Look at it. That's this guy here. C-sec forces theory and calculations. Watch that video. Everybody needs to know about forces to pass their CXC exam. All right? So try to have it watched and ready for next week so I can give you a small mini test on it. It's going to be a very easygoing test, but still a test. All right, guys. So I hope that made it a little bit clearer, and see some of you all tomorrow for chemistry. Come prepared, right?